Now we will move on to the unit 2. Unit 2. See, coming to unit 2, this is how your syllabus is. Okay, you almost have how many? Here you have 7 topics, I guess. There are, yeah, 7 topics. Okay, you have 7 topics in unit 2. There are 7 different topics. So first one will be like your composite slab, and then after composite slab, I'll deal with composite cylinder. This is cylinder. Although it is given as hollow cylinder, we'll look at it as a composite cylinder. Then sphere. This overall heat transfer coefficient, electrical energy, critical radius of insulation will deal accordingly whenever required in these 3. Okay. Next concept will be your variable thermal conductivity. Then systems with internal heat generation. These 2 we can close them very fast. And first 3 and next 2. Okay. These 3 and then these 2. Okay. They require a lot of time. These 3 and this. Okay, these 2 we may finish a little fast, but these 2 and these 3 will take time. So kindly keep this in mind. I'll be going little fast compared to your first unit to cover all this. Okay. Now let us look at the composite slab. What is use of boundary condition? Let me explain that with a real-time example. Now, what I have drawn here is a wall. This is a wall of your room. Okay. This is wall of room. Any room you can take. If you take it now, what happens is you will have a certain temperature T1 on one side and certain temperature T2 on the other side. Okay. So this is your thing. If I have to represent this particular heat transfer that is happening in this, what I have to do, I have to take governing equation. Okay. First thing in the process of defining a heat transfer problem mathematically is to take the governing equation in the first place. When I take the governing equation in the first place, what happens is, this is a rectangular coordinate system. Since this is a rectangular coordinate system, what it will be, dou square T by dou x square plus dou square T by dou y square plus dou square T by dou z square plus q gen by k is equal to 1 by alpha into dt by dt. Small t I can take, small, some textbooks have tau. Anyways, so this is the thing, and this governing equation is representing the heat transfer in this phase. Now, if you look at this wall, will have temperature variation only in this direction, that is from inside to outside. Okay, this direction it will not have heat transfer, that is your vertical direction, that is y direction. So this can be neglected. Same way, in the direction perpendicular to this, that is z direction. In z direction also, the heat transfer will not be there. Internally, there is no chemical reaction happening in a wall, or what do you call, nuclear reaction, anything of that sort is not happening. So this will be 0, and this will also be 0. This is more or less steady temperature. Okay, temperature on the wall is not varying with time. So only what you have here is dou square T by dou x square is equal to 0 is your governing equation. Now that you know governing equation, to solve any given governing equation, you should have something called as general solution. Okay, you should have a general solution. How do I get the general solution? To get the general solution, what you should do is you should integrate this one. Okay, take out this differentiation out of this. To take out the differentiation out of this, what I will do is I will integrate. When I integrate that, what I get is dou t by dou x is equal to C1, I can say. So this is what I will get. Basically, when I differentiate this one, no, I will get this. That's why when I integrate this one, I will get this. So reversal. Okay, differentiation. You'll get this. Integration, you'll get this. Okay. Now, this is the equation that you have here. Now, I want to further integrate it. When I integrate it, I have to take it like variable separable. Dou t is equal to C1 into dou x. If I do integration now, integral dt is t is equal to integral dx is x. So what I get is C1x. Since I'm not taking limits, I have to put one more constant here plus C2. So this will be your general solution. Okay. See, first what I have taken is first is my governing equation. In first place, to solve any heat transfer problem, you should have governing equation in the first place. This is the first thing. The next thing is general solution. Okay, when you do some integration, you'll get the general solution. This is your general solution. In this general solution, you have something called as arbitrary constants, C1 and C2. Okay, C1 and C2 are called as arbitrary constant. To solve this arbitrary constants, you have boundary condition. Okay, so that is what the use of your boundary condition is actually. So the boundary conditions will help you find out what is C1 and what is C2. Let us see this. Okay, this general solution you have, let me call this equation as 2, so that this equation is can be called 1. Now let me take the boundary conditions. Okay, what will be the boundary conditions for this one? Here this is x is equal to 0. Here this is x is equal to L on the other side. Now the boundary condition will be the temperature boundary condition or the Dirichlet boundary condition, which I can express it like yet x is equal to 0, the temperature is equal to T1. Yet x is equal to L, the temperature is equal to T2. Let me call this as 3, this as 4. Now what I will do is I will take these boundary conditions and I will substitute into this equation 2. So let me take 3 in 2. If I do that, what I have is T1 is equal to C1 into 0 plus C2. So what it gives you is C2 is nothing but here T1. And then if I substitute 4 into, what I get, T2 is equal to C1 into L plus C2 I will get. So this will be like T2 is equal to C1 into L. This C2 I can write as T1. So the C1 will be equal to T2 minus T1 by L. So now I got what is my arbitrary constant values. It is C2 and C1. So what I have is general solution T is equal to, in place of C1, I will write T2 minus T1 by L into X. Plus in place of C1, I will write T1. So this is nothing but T is equal to C1x plus T1. This is something like Y is equal to mx plus C. This should be C2 actually. Yeah. C1x plus C2. This is actually your y is equal to mx plus c, a straight line equation representing a linear variation of the temperature. So in the case that you have taken, what you can understand from this equation is you can understand that the variation is linear temperature variation. Okay, this should also be written here. So the case taken, linear temperature variation is happening here. So this will be your general solution, wherein you will have the temperatures also into this equation. See, what is the use of your boundary conditions? The boundary conditions, they have converted your general solution of arbitrary constants into a real case. Okay, how it has created a real case, let me tell it with an example. The same wall boundary condition, wall case, wall. This is a wall case that we have taken, one dimensional case. Let me draw this properly. This is why I'm putting it like this every time, is it is representing the wall is infinite in this direction. This dimension is important to me, not this dimension. That is what the representation there. Now, inside you have 15 degrees centigrade. Outside you have 4 degrees centigrade. See, these are the values that I've taken from the problem that we have solved for the conduction case. Okay, 15 inside is there, 4 degrees centigrade is the outside temperature. This is the first problem that we have solved in our course actually. So the same problem I have taken it here, 15 degrees centigrade on one side and the 4 degrees centigrade on the other side. If this is the case, and the thickness is 1.4 that we have taken. Anything you can take. One example is important here. So now, look at this. I can substitute T2, T1, and L. This is T1, this is T2, and L is there. Now, if you look at this equation I can transform it into like T minus T1 by T2 minus T1 is equal to X by L. Okay, this is a simple way of writing the same equation. Okay, see, the beauty of this equation is this equation will help you find the temperature at any given x. Okay, temperature at any given x. At this x you know, at this x you know. In between you don't know. Okay, to find out the temperature in between, maybe at 1 meter you have to find, maybe one halfway you have to find 1/4 or 3/4, anywhere if you want to find, this equation will be helpful to you. How it will be helpful to you? Let us say at 1 meter, if I take, what will be the temperature at 1 meter? Temperature at 1 meter. I will write it like temperature at 1 meter. What is the value? If I want to find out, see, it will be like temperature at 1 meter minus T1 is 15 and T2 is 4 minus 15 is equal to X is 1 meter and the whole thing is 1.4. Everything can be substituted into it and I can find T1 meter. It is as simple as that. So what I'm doing is using a governing equation and after governing equation, I've got a general solution. Converting this general solution into an useful solution using the boundary condition, I have got a real solution. Okay. So the thing is, in any heat transfer problem, the steps are this. You will have a governing equation. Once you have a governing equation, you can have a general solution. This general solution can be converted into a practical problem using boundary condition. Okay, these are the 3 things that you should keep in mind while solving any given heat transfer problem. First governing equation, then general solution, then boundary condition. So that is what the use of boundary conditions that I was speaking to. These 2 alone cannot help. Okay, These two combined with the boundary condition will be a great help to you. So to start with this composite slab, what I'll do is, let me start with the electrical analogy. The electrical analogy. See, in your electrical analogy, what you have is, this is a wire, there is a resistance here, okay, and there is a potential difference existing between these two. This is V1, this is V2, and you have a current flowing, and because of this, there is a resistance here. Okay, if you take any simple circuit, this will give you V is equal to IR. V is equal to IR is there. I will write it like R is equal to V by I. This is how I'll write this. And the same thing, I will take it as a, an right here. What I'm doing is I'm taking a similar analogical heat transfer case T1, T2. Okay. Here, heat is flowing. Here, I have temperature difference. So, analogous to your temperature difference, you have voltage difference here. So, if I write the same equation here, in place of potential difference, what I have is T1 minus T2. In place of I, that is flowing, current is flowing here, heat is flowing here. So in place of I can have Q. So in place of resistance, I'll introduce a concept called thermal resistance. Okay, this resistance is electrical resistance. This resistance is thermal resistance. So why did I take this electrical analogy? To bring in a concept called as thermal resistance. Thermal resistance is a very important concept in solving any given circuit. Okay, so the thermal resistance is equal to T1 minus T2 by Q. Okay, this is how it can be taken. Can I express this particular T1 minus T2 by Q in a different form? Okay, without measuring any temperatures, can I find this? If I know the thermal conductivity, yes, I can find it. See, this particular expression, what I have is, if I write the Fourier's law of heat conduction, Q is equal to K into T1 minus T2 by, here I should have A, L. K into L. So if I transform this equation will turn out to be T1 minus T2 by Q will give you L by KA. So what I can write here is L by KA. So this is one particular formula for your thermal resistance. This is the other particular one. This one will use the heat transfer and the temperature difference. This one will use the L by Ka. Here, geometry is taken into consideration along with your thermal conductivity. So either you can use this expression to find out thermal resistance, you can use this expression to find out the thermal resistance. Anyone you can find, so anyone you can use. So what is the unit of thermal resistance? Can anyone tell me what is the unit of thermal resistance here? You look at this equation and tell me what is the unit of thermal resistance. Can somebody respond? It is Kelvin per watt. The numerator, the unit is Kelvin, and the denominator, the unit is watt. So it is Kelvin per watt. So the thermal resistance is measured in Kelvin per watt, right? Now, What I will do is I'll apply it to a composite slab. I'll take a composite slab and I will apply this, you know, I'll apply this concept to this composite slab. So what I will do is I will take two layers of wall here. This is wall A, this is wall B, and there is a temperature drop here, and there is a temperature drop here. Let me call this T1, let me call this T2, or this one as T3. And this having the thermal conductivity Ka, this having thermal conductivity Kb, and this having thickness L1, and this having thickness L2. If this is the case, what I can write here is, if I have to write Q here, in this case, this is equal to the T1 minus T2 by RTH, I can write. How can I write this? See, the same thing if you take now, this expression, if you look at, this is Q is equal to T1 minus T2 by L by Ka. That is equal to T1 minus T2 by RTH. L by Ka is nothing but RTH. So this one I can take it this way, or simply RTH is equal to T1 minus T2 by Q. Anyways, the same thing you will have. So what I can write here is, I can write this as Q1 that is entering here, and Q2 that is going into the second one. So if I have to write Q2 here, this will be like T2 minus T3 by RTH2. Let me call this RTH1. If I write the same thing here, T1 minus T2 by this in terms of L by Ka, L1 by Ka into area. The area is anyway same for both the things. So what I can write is area A is equal to area B. The contact that is shared by these two is same. So the area perpendicular to the direction of heat transfer is same in both the cases. So here if I take T2 minus T3 by L2 by KB into A. This is what I can have here. Now, if I take this overall Q overall, this has to be written in terms of the initial temperature and the final temperature. Initial one is T1 and T3. So for that, T1 minus T3 by RTH1 plus RTH2. This is how I write this. See, how did I get this? Okay, how can I write this thing like this? This also I got by electrical analogy itself. See, for any given this kind of problem, this should be better. Okay, any this kind of problem, you draw this circuit diagram, and then you represent things here. Okay, here L by Ka you will have, this is L1 by I'll write it RTH1 for simplicity. This I'll write RTH. So what I have here is T1, T2, T3. See, what I understood from this case is, this is like a resistance in series. a resistance in series. If you have resistance in series, what you can do in your electrical circuit, you actually add them. Resistance total will be equal to R TH1 plus R TH2. So the same thing I have done, and I have substituted this here. So when you go with resistance in series, you simply add the resistances. So I have added them. So this will sum out to the Q overall. So this is one particular case of your composite slab. Similarly, we can take one more case here for the composite slab. If the given things are in parallel, what you should do. Okay, let me take it like this. This is a bit complex case compared to your previous one. So here I am taking three thicknesses. This being your L1, this being your L2, this being your L3. This is material A, material B, material C, material D. If this is the case, what will be my resistance diagram? Look at the circuit diagram I have to draw. So the circuit diagram will be like this. Like this will be R with respect to A. And then what you can see is B and C are not in series. They are in parallel. So what I have to do is I have to write them in parallel. I have to represent them in parallel. So this will be RB, this will be RC, and RD is again in series. So this will be your resistance circuit. Here, in this whole thing, the temperature maintained is T1. In this whole thing, the temperature maintained is T2. So the whole thing, the temperature maintained is T3. Here, the temperature maintained is T4. So what I can represent here is T1, T2, T3, and T4. This is how your resistance circuit will be. Once I have this resistance circuit, next thing to do is Q is equal to initial and final, that is T1 minus T4 by by the sum of the resistances. Okay. If I take this one, RA, I can take. See here, R effective of these two I can take. I cannot simply add these two here. So what R effective we will see, and then RD will have. So to get this R effective, I'll use a concept called as a resistance in parallel. Resistance in parallel. If the resistances are in parallel, what you will do is 1 by R effective is equal to 1 by RP plus 1 by RC. So this is what you will do. Okay, this is what you do in your electrical circuit. The same thing you are doing it here. So R effective will be equal to RB into RC by RB plus RC. Okay. So this is how you will get this. So this Q will turn out to be T1 minus T4 by RJ plus RB into RC by RB plus RC plus RT. Okay. When I write R, this will be R thermal only. Okay. So this is how you will get Q overall in this particular case. The case can vary, but based on a given case, you should be in position to draw this resistance diagram. Once you draw this resistance diagram, the things will be clear to you. you can actually write all these things. Okay. Apart from this particular queue, you can also write the remaining things also. Let me put out this particular thing again in the bottom. Okay, I have this diagram again here so that I can write what is your queue. Queue, one way of writing it is as it is in the top. Okay, T1 minus T4 by R total. This is one way. The other way of writing this is T1 minus T2 terms also you can write. The same thing will be equal to T1 minus T2 by RA. The same thing will also be equal to T3 minus T4 by RD. This is one thing. Another thing is T2 minus T3. T2 minus T3 by R effective. This R effective is nothing but T2 minus T3 by RC RB first into RC by RB plus RC. So this is your Q. The same Q, you can write it in various forms. Okay. In a given problem, he might be giving you these two temperatures. And if you know these two temperatures and resistance, you can find out Q. Once you can find out Q, you can find out the remaining temperatures using these three equations. So it's like that. So in a given problem, you should be in position to represent this in a circuit diagram. Once you represent this in a circuit diagram, you can write all these things very easily. So if I take RA here in this particular in this particular case, RA if I take it is L1 by KA into the area A. The area is whole area if I take here. Okay. Same way I'll take it for RD. This is EL3 by KD thermal conductivity of D into A. The area is same for both the things. Now, what should be the formula for RB? And what should be the formula for RC? L2 by KB anyways I will have. Here also L2 by KC I will have. And then what is the area here? That is the question. See, the area will vary here. Okay. If this is whole L now, if this is whole area now, if this may be like you can have this as A by 2. This is A by 2. This is complete A. This is the whole area representing the whole area. So this will be A by 2. This will be A by 2. In a given question, he can give A by 3, A by 4, anything. Okay, this is 1 by 2, 1 by 2 here. It can be 3 by 4, 1 by 4. 1 by 3, 2 by 3. Like that, anything he can give in the can be giving you in the question. This part is very important. This question, this part of the question, many students will miss that I have observed.